Greetings of the day, everyone. So today I, Shivam, will be discussing my work around group fair clustering. So mainly we will be looking at some of the notions and then we will be looking at one of the efficient algorithm for the same. So this is a joint work with Ganesh, CKN and Shweta at different affiliations, and we would like to acknowledge SERB and PMR funding for funding the project. So as we know that nowadays machine learning is being used in a lot of decision-based systems, but we have come to know that these decisions can be biased towards certain people. Like it was seen in Compass controversy, that is the system was giving high risk prediction scores to black people compared to white persons in US court trials. So such decisions can have long lasting impact on the humans, and this has led to study of fairness in supervised and unsupervised learning. Currently, there is a plenty of work happening in supervised learning, but the work in unsupervised learning is in native stages. So mainly we will be focusing on unsupervised learning. Let us look at one of the motivational use case. Let's say that an organization wants to open up offices across a country and mainly it wants to minimize the travel time. Now, one can formulate this problem as a clustering problem. But there would be one very simple problem with the solution, that is the traditional solutions might result in, let's say, grouping people, similar people, that is all males into one office. But any organization will not require that. They would require that certain diversity is maintained. So to formulate these diversity constraints, that is, let's say, minimum fraction of males and female in each cluster, we add these as group fairness constraints. So how to tackle this group fairness constraints? So to this, different notions came up in the literature. The first one was by Cincinnati et al. In 2017, and it was called balance. Mainly it dealt with ratio, it was limited to binary groups, and it dealt with the ratio of males and females in each cluster. Let's say that in the diagram given below, the ratio is 1:2. That is, for each one red point, there are two green points. So this, since we know that this was limited to binary group, Dera et al. In 2019 extended this notion as a lower and upper bound kind of setup in terms of cluster sizes. But still, these all notions led to some of the state of arts, and these were as follows. Like firstly, Cincinnati came up with a fairlet-based approach, but it was having a huge time complexity. Though Becker et al. Reduced the time complexity, but again, it led to a huge increase in space. Rico et al. In the following year came up with an optimization-based solution, but these optimization-based solutions were requiring a lot of hyperparameter tuning, and even linear programming-based solutions were computationally expensive for some certain objectives like k-median. So to this, we came up with our own notion of fairness rather than going into something. The main problem in existing notions was that they were going into something which is not known to us, that is the cluster sizes itself. So here what we did, we came up with something which is known. So we know the dataset composition, which is the source of the bias. So we formulated what we said, that for each group, let's say a group A, we want certain fraction, tau A fraction, to be present in each cluster. That is 10% of red points should be present in each cluster. So let's take one example. Let's say that in the instance shown, the balance is 0.25. And similarly, let's say that lower and upper bound on green color is 3 and 12. But when we are coming to TOR ratio, now we will be formulating it as certain percentage in terms of data set size. That is 20% of my total green points, which are 15, I would require them in each cluster. That is 3 green points should be present in each cluster. Similarly for red color. So now, since we have proposed a new notion of fairness, we need to show that it is a better notion. So for this, we developed closed form relations for different notions, and we said that satisfying TOR ratio fairness will imply that all other notions are satisfied. So next, what we did was, there was a very interesting lemma which was given by Bera et al. What they said is that if we convert our clustering problem into an assignment problem, then solving our assignment problem will not be too far from our clustering problem. That is, it would be only alpha plus 2 approximation factor away, where alpha is the approximation factor of any clustering, NP-hard clustering. So this notion was limited to balance. We extended it to TOR ratio fairness. Now our problem is only limited to solving the assignment problem. So for this, we came up with a simple round robin based algorithm. So it starts something like this. Let's say that we are having two cluster centers, C1 and C2. They might be coming up from vanilla clustering. And then what we will be doing is that we will be finding the distance of all the points from these centers. After finding the distances, we will be sorting these points based on the color, and within same color, we will be looking at the distance. So this would be giving me some preference order of C1, let's say, to all the red points and C1 to all the green points. Similarly for C2. Now what we will be doing is we will be coming up with some, we can say, center ordering. Let's say if C1 followed by C2. So I will be going to C1. I will be asking what is your best point. So it would be saying my best point is C. I would be allocating C1 to C. Similarly, then I will be going to C2. I would be allocating A. Next, I will be going back to C1. In this round robin fashion, I will be assigning all the red points up to my threshold when till the point my tau ratio is not fulfilled. After that, I can purely assign based on distance. After solving this problem for red points, I will be going to green color. So we call this algorithm as FRAC OE, fair assignment over the end. And we proved that this algorithm is a two approximation algorithm. And after that, the intuition behind the proofs were like, we came up with some bad assignment. So bad assignment would be something of the form of cycle kind of thing, where we would be showing that data exchange combinations that might be possible. Let's say, for example, in the instance shown, we are showing it for k equal to 2. So we were using triangular inequalities to and mainly the properties of round robin algorithm to bound these factors. So next, we show that this algorithm has a 2 raised to power k minus 1 approximation solution for journal k. But the existing open problem is that we can prove it to be 2 approx. And right now we conjecture that. But we show that the guarantees are tight with respect to this. And we have an instance for that. So next, coming to the experimental section. Here primarily we show that our algorithm is able to achieve state-of-art performance. 1 second. So yeah, so we can see clearly from the comparison that our algorithm, which is black in color, is able to achieve quite lower objective cost, and it is able to maintain the stricter balance. And at the same time, in the fairness error, it is almost negligible, near to 0. So next, coming to when we are varying the number of centers, so we can see that the performance does not degrade over time. Similarly, we can see that in the algorithm, we took some center ordering. We in this experiment show that the center ordering will not play a much bigger difference, as the variance in the center or over different permutation is quite small. Also, coming to the runtime, we can see that our runtime for FRAC OE is quite similar to vanilla algorithm. So it is computationally quite significantly better than Bera and Zico. So these are some of the key takeaways, and so some of the future directions that we can extend the work to multiple groups, and we can look at amalgam of different fairness notions. So these are the references, I hope, and this is the reach us emails, and you can even query us for any of the doubts. Thank you.